Welcome to this presentation. I'm Pere, I'm a solution architect by Confluent, and this is a collection of stories from operating Kafka at scale. So we're going to start by reviewing a little bit what are the internals of Apache Kafka. Before you actually start operating anything at scale, you need to understand what's going on internally. Then we are going to see as well 4 different categories of things that can happen that are actually things that are happening in real life to every one of us. I'm going to review a little bit some observability tips and things you have to monitor in order to take care of this stuff, and then a quick recap. So the first thing, understanding the magic behind the system. What is really Apache Kafka? Apache Kafka is a distributed block where you can actually write things, where you write things at the end and can read things from many places. And this property gives us a very good characteristic from the system, and it's scalability. Because we can have many readers consuming data from different stages of the log, and the performance is always good at writing because you write at the end of this log. And you can see this as well as a structure that it's used to build up other systems. Like if you are coming from the database world, you can know the write ahead block, and that's actually the same idea from databases. But what is actually Kafka internally? Kafka internally is a highly distributed system. This is only the internals that are involved in the brokers. You can see the brokers in lila color. You can see different other systems. In here, in the red area, you can see the brokers. The brokers are represented in lila color. They are the unit that stores your data. In Kafka, there is something called topics, and each topic is partitioned. What it means is that a part of this data is separated in different chunks, and then every partition is replicated. So we get to have a copy of the data in different locations. In the blue color, you can see here the leader replica of this partition, and in gray color, the followers. On your left side, you can see three very important components here. You can see the log compaction, and the replica fetcher at your very left. The log compaction is the class that is responsible of the housekeeping, of the data housekeeping in each of the brokers. It is responsible of compacting topics. It's a specific characteristic of a Kafka topic where only the latest message is being it's present, and you can see the replica. In the log compaction, you have as well the capability to delete a message and basically doing the data recollection there. The replica fetcher is as well very important because it's the thread, it's the Java class that is responsible of pulling data from the replicas, from the followers to the reader. And if this, for example, the replica fetcher is not behaving properly, you can see like the followers are not having enough messages replicated, and they have problems. One class as well that is, or property that is very important from Kafka is the controller. The controller will be responsible of holding the state, of knowing everything that happens in the Kafka cluster, and not just that, but making decisions, saying which partition is the leader for every subset, and for example, who holds what and when, and talking to Zookeeper. The controller holds this cluster state, and only one should be there, because if 2 people make decisions, then there is always problems. On the upper side, in green color, you can see the Zookeeper. What is Zookeeper? Zookeeper is the decision maker. It's a distributed key value store that it's been around for years and years already, and that Kafka uses for two businesses. One is to store metadata, things like the mapping where each partition it's living, so the partition to broker mapping, and as well to make decisions. So for example, to decide which node, which Kafka broker is going to become the controller. So it's very important. The health of Zookeeper is critical for the system. On the left-hand side, you can see the producers. They are the classes that are implementing your application and are the responsible of writing data into Kafka. And on the right-hand side, you can see the consumers. The consumers are the classes in your application that are reading data from Kafka. They are grouped in something called the consumer group. And that's a very important concept because it's responsible for scaling out the consumers, allowing multiple copies to be there. And for example, when one consumer is not behaving anymore, you can restart it. How does it look internally in the broker? Internally, it looks like this. This is actually what is called the anatomy of a request. A message comes from the network into the broker and is held and is received by a collection of what is called the network thread. The network threads will receive this message and put it in a request queue. From the request queue, a collection of IO threads are going to read these messages and put it into the page cache. From there, they are sent to the purgatory in case the replication needs to happen, because remember, we have partitions that are replicated across different brokers. After replication happens, they are sent through using the network threads back to the response queue and to the original client that sent this message with the result, acknowledge or not acknowledge. Why is this flow very important? Is because it maps everything that happens in Kafka. As someone has told me many years ago, Kafka brokers are not that intelligent, are very simple. They get messages, they put message into the page cache, and then they respond to the original message. The really, really intelligent component in Kafka are the clients, the really smart ones that make decisions where to send, etc., etc. This is as well very important because when, for example, the disk doesn't work quite well, all of these internal states are monitored. So if the disk doesn't work quite well, the request local time is going to increase, the IO threads are going to be more busy, and then all of these things might be piling up upstream, showing a correlation between request local time and request queue time, etc., etc. So all of this is monitored in Kafka. All of this is available for you as a JMX metric. The first story that I'm going to tell you today is about durability. Story number one. In the happy path, in the best case scenario, a producer sends a bunch of messages synchronously or asynchronously to the broker. The partition leader will receive this message and update the open segment. If the topic has more than one partition, then the replication will start. The received message are now committed, are now safe and stored in all places. And then no exception is going to be returned back to the client. And the producer can continue sending messages. But that's the happy path. But bad things happen in distributed systems because we work with a lot of machines, because of the network, for many reasons. That's why it's amazing to work with distributed systems. That's a very simplified case. A producer is sending messages into Kafka. They are buffered. So it means they are together and they are batch and buffered. So they are pulled a group of them are pulled together to be optimizing the network throughput, and they are buffered. They are stored for a while until this combination can happen. Then they are sent into Kafka. In that case, we have only one Kafka node. So we have all the data in only one machine. what could go wrong here? Imagine if you lose this node. Then the producer is not able to send any data into this broker. And the usual reaction is this one. Oh no, my data is only in one server. So even if you thought it would be possible, have always multiple servers. And that is actually a very common deployment at the beginning with Apache Kafka, 3 brokers. The producers, in that case, will send the messages. They have the producers a very special variable that's the acknowledge level. And this works in a way to control how many durability do we want. With 0, it's going to be fire and forget. With 1, it's going to be acknowledge when the main partition is storing the message properly. And with all, it's going to wait for all the replicas to do the replication. Keep in mind always one thing. The default in Kafka are acknowledge 1, replication factor 1, and min sync replicas 1. These three values are chosen prioritizing one characteristic and over the other one. But if you're looking for durability, you need to make sure that data is always copied in many places. Remember, Kafka is optimized at the beginning for availability and latency. So data can be sent very fast and everything is very available. Over durability. If you want durability, durability is achieved with replication. It's always very important to remember. For durability, always replicate data everywhere, in more than one place, possibly in 3 places. If you have multiple data centers, replicate data over different physical locations. And this you can achieve with Kafka, and always use acknowledge all. So all your replicas have to have received the message from replication in order to say thumbs up. The second story is under-replicated partitions. This is a very common thing that happens to all of us from time to time. So what are under-replicated partitions? All writes, at least all writes and reads goes always to the primary partition. Reads not anymore because of the allow consumer to fetch from closest replica. So the KAP 392. But we can assume that for now, still all writes and reads goes to the primary. Once the data is received, the replication process starts by the replica fetcher thread. So you receive the data, and then this thread that we spoke about earlier gets all the data back to the replica, to the different replicas. And a response is sent back as soon as all required replicas has replied the message. But what happens if something goes wrong here? So remember, this is the anatomy of a request. If for any reason one of the replicas is not fetching enough data or at the right speed, etc., the message is going to stay in the purgatory for longer. And then the remote time is going to increase. And the next thing you're going to see is that they fall back and cause an under-replicated partition. That another replicated partition is nothing else than a partition that is not up to date with its main partition. So that's the case of under-replicated partitions. You start seeing an increased number of under-replicated partitions. Remember, partitions that you cannot, that are not keeping up with the mine. Even a few of the topics could be offline now. If you stop your producers, the cluster does not heal over time. So stopping producing data does not help. If you restart the problematic nodes, everything works again. But when you start producing data again, you go back to under-replicated partition. In that case, that actually happened to me with one of the customers I work with. The Kafka cluster was in version 0.11. The network and IO utilization was completely normal, so no hint on the utilization of the network threads, and the issue does not heal by itself. Remember, in that case, there are cases, situations where the under-replicated partitions might be something transitory. We're seeing actually this logs lines in our server.log offset out of range, replica fetcher, exit because log truncation not allowed, etc. And this was a hinge that the replica fetcher was having actually trouble. We actually hit that bug, Kafka 5634. It was very easy to reproducible, creating a replicated topic, configured with compact delete, and just basically hammering with a lot of data very fast. Yeah, and that actually was a bug that was caused because the high water mark and the lock and the latest offsets were changed. So when we're actually change around. When the replica fetcher was trying to fetch more new messages, it was confused and it raised an exception. The cluster will not recover because of this. The data and the watermarks are broken. The only solution, to avoid this problem was to update to a newer version. And that gives me to something cool with Kafka is the upgrade process is really easy, can be rolling to start. So you can embrace a policy of updating very often. And that's actually a good thing because the project changes quite a lot. The next story is about partition reassignment storms. Have happened to all of us that we wanted to move partition from one node to another one, and we forgot to throttle. And then we got a storm. Remember this situation. Is your throughput low? Your expected consumption throughput and even the production throughput is going down. So you decide to scale out and create new partition. But the problems are still there. See this image. When something happens regarding partitions is because of the number of leaders. Remember what we explained before. Blue partitions on your top area are the leaders and gray are the followers. Kafka node number one has a lot of leaders. So every write and until the addition of the latest KP for reading from followers, all the reads will go to Kafka 1. So it will be overloaded. So the throughput on Kafka 2 is going to be actually zero, only for replication. Yeah, and we will see a mismatch in this here. What you would probably do here is rebalance this thing, move some of the followers from Kafka 2 to Kafka 1 and move some of the leaders back to Kafka 2. Or a natural reaction to this, maybe add a new broker and reassign some partitions. You can do this with the Kafka reassign partition tool or with Confluent rebalancer. Because we need to move it. When Kafka has a new broker, as of now, it still needs to move and some of the old partitions manually there. However, this scenario can be overwhelmed. Remember, all the replication, everything happens to the network. So when we are moving partitions, we do it over the network. And we have a given set of network threads that we have configured. So if we overwhelm the brokers with replication load, then you are not going to respond basically to your normal request. And it's very, very important to throttle this. And in the older versions, this was not possible. Solution for this, or things to always keep in mind when you do partition moving, is work with a smaller number of partitions at a time. Try not to overload your systems. Take advantage of replica throttling. Especially in the latest versions, everything in replication can be throttled. You can use as well tools like Confluent rebalancer that helps you with all the mathematics needed in order to calculate which partition to move to where, taking into account space, taking into account usage, etc., etc. That's a very cool tool to automate and make elastic architectures out of that. The moral of this story is use throttling. Always when you implement anything that moves data or does consumption, use throttling. As well, please implement quotas in Kafka. It's a very nice feature that will segregate a bunch of network thread and IO thread percentage usage for a given client. And this will prevent quotas and throttling that you have a problem like this. Second moral of this story is use JMX. Monitor everything. Maybe it's not something that your management is going to like from day one because it's not providing a business benefit. However, it will save you a lot when something goes wrong. Every time you change as well your data flow, so you change your producers, you change your consumers, test it out. Try to test everything in a staging environment that looks like production. You want to avoid causing trouble in production. And fourth story. This story is actually very, very important. Well, the other ones were very, very important as well. But this is one that sometimes people forget. Your system is important. A scary one. A story that could happen to you. Your Kafka cluster is deployed in multiple data centers. Maybe you are into one of these scenarios. One of your data centers is down. Yeah, this never happened to anyone. Yeah, sure. Happened to a lot of us. You are doing disaster or you are doing a disaster recovery drill. Or even more Kafka. Actually, something happens to me in real life. In one of the companies I used to work before, someone just turned off a machine. And then you are losing one node. Remember, your Kafka clients, that are the smart ones, have classes and ways to connect to the brokers. They will ask for metadata in order to know to which brokers to talk to. And they will use this metadata based on the Bootstrap servers list, actually in order to decide, for example, where is a primary partition that they need to write to, or where is anything. This list is shuffled at the startup time and is organized based or prioritized based on the in-flight requests that are computed, sorry. You actually saw this kind of logs. Client is not ready to send, blah, 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 mass delayed, big number of millisecond, and the second line, very similar. This was an indication that something was going wrong with the client, yeah? And this could be, by the way, this is admin client, but could be any other client. At the end, admin client is using the same classes that the network client to talk to the brokers and fetch the metadata. And you thought, okay, I'm only giving it one broker. Let's give it the full list of brokers. Everything still fails. So what actually happened is, remember I told you about this network client class? This is the responsible of talking to the brokers. And till now, it relies on the operating system parameters for socket timeouts. And this problem was caused because we tried to talk to a broker that was down, but the network client was still not able to decide and was sticking to this broker because even if it wasn't reachable, was sticking to this broker and not able to decide. If you find this problem, it's very easy workaround, and maybe even your standard operating system provided to you by your system teams might already have this corrected. You need to do the TCP SYN timeout and the TCP SYN retries because usually they are very big. This, by the way, is going to be fixed in the next release of Kafka with instruction SKP 601, where the network client on the client side will be able to have specific timeouts and avoid using the global ones. So if your clients are not reaching your brokers and you are in one of these scenarios, always think about the network. And that has a model, this story as well. Even if you were monitoring our application, this was something that at the end was happening in my operating system. So it's very good to always take care of your operating system. Things that could happen as well in that case, DNS names or URIs in that case. Happened to me sometimes where someone introduced an underscore. That was a case where it's not valid and broke everything. Or one that is actually quite interesting is if you are operating with Red Hat 7 or 6, there is something called huge pages. And because Kafka writes into the page cache and then gets operating system to flash, bigger page cache pages causes Kafka to be lower performant. So disabling actually the huge page memory in Red Hat does a big increase. Your system appreciate it, take care of that. It's very important for your overall Kafka performance. Last but not least, we said we're going to talk about observability. So how do I monitor everything like this? The first thing you should be always monitoring is the threads that are handling your request. And these are the request handler and the network processors. Here you have two JMX metrics. And these are the very important metrics to process and to have. Just remember, they are idle %. So it shows the time that is being idle. And it's always going between 0 and 1. The next thing you have to monitor always is the connections to Zookeeper. Remember, we spoke about Zookeeper, that Zookeeper makes decisions in Kafka, and that is very important to keep it alive and healthy. So it's very good to monitor broker to Zookeeper disconnects. If you start to see disconnection between broker and Zookeepers, that's bad. If the latency increases, it's bad as well. So the average latency should be always maximum 10 milliseconds. If it's bigger, you might be in trouble. And just remember, Zookeeper is very sensitive to latency. And every time that controller needs to make an update on metadata or needs to make a decision like battling for who is the controller, it's going to go right into Zookeeper and check Zookeeper. Another that's very important is the number of connections. So especially if you are sharing Zookeeper with multiple clusters or with other systems, just remember, num-alive connections. Try not to go bigger than 0.7% of your current possible connections, or you will be in trouble. Last but not least, we have to monitor the partitions. We have to monitor the availability of our data. And this you do with the offline partition count that tell you if there is and how many partitions are actually not reachable at all. Under replicated partitions, just remember this is a canary, but it's a very good canary. When this doesn't recover quickly enough, is the indication that something is happening there. And last but not least, the min-in-sync replicas. These are partitions. All of these three variables are things you can pull from JMX, and they will give us information of where, how is the state of my partitions and my replicas. Talking about partitions, it's good to talk about the count of partitions. So the global count of partition and the partition that is held in every broker. Just remember what we said at the beginning. Controller talks to Zookeeper, and controller holds the mapping between broker and partitions. So, but it holds as well the in-sync replica list. So when any time that partition falls out of in-sync replica list, or partition is being moved, or there's a change on the partition, it has to talk to Zookeeper to update the metadata. If we have a small number of partitions, that's not a problem. But if we have 200,000 million partition, then even a very small change is going to be 1 millisecond multiply big number. That's the thing we have to control. So take into account this latency situation, and it always correlates with the total number of partition per cluster and per each broker. And that's the variable that you can control how this thing is performed. And remember that before we saw that you can monitor the latency when it talks to Zookeeper. But now we spoke about metrics to monitor in Kafka that are system related. What about my business? My business wants to know if the thing is actually going as it should be. It's very important to monitor as well the consumer lag. And the consumer lag is nothing else that says how far behind is each consumer to be up to date, to actually having written everything. And you can do this based on offsets. So basically saying, I'm behind 3 offsets, or timestamps. I'm behind 3 hours. Because we can get a message every hour, then you are 3 hours behind if you are 3 offsets behind. For business, it's always very good to have time-based consumer lag, because it's a metric that it translates literally to how far behind, and it translates literally to RTOs and RPOs that every disaster recovery scenario and resilience is talking about. There are simple ways to monitor that. The more simple way and more naive is just pull the JMX from all the consumers, but that's bad. Remember, each consumer as well, like the brokers, give you JMX metrics to monitor, but it's only active while the consumer is running. So you cannot have this information when the consumer is not active. Another simple way to monitor this is using the Kafka consumer groups. They are living in the broker, but they have a similar problem. The information is only available when the consumer group is up. There is one very nice way that is a way to pull the previous 2, plus adding some intelligence, is the one that's implemented with LinkedIn, the project LinkedIn Portal. And this project I really recommend. It's a very old project, but it's still quite up to date. And the rules are just amazing. So just go check it out, the wiki page, and you will see like a collection of rules. If the lag with the window is 0, etc., etc., etc. And the best approach to, actually for me to evaluate this is timestamps. And because then you can say and report to the business, the consumer lag is X number of hours. And this you can achieve with Conflict Metrics Reporter and Control Center, and will give you a very valid and very positive and business-related metric to report back to your business counterparts. Last but not least, we said system is very important, so please monitor your system, please, 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 please. And for this, you need to monitor CPU usage, disk availability of file handlers. The easiest way to shoot up your broker is consume all the available file handlers for your servers. And nowadays, we only run broker in one machine, so not a problem. IO consumption, network consumption, all of these 5 metrics are critical and should be always up to date. Probably the 2 more important ones that happen to me to see brokers down is disk space and availability of file handlers. Just please remember, always monitor your system as well. If you're running this on top of another system, you're not running this in bare metal, you're running this in Kubernetes, VMware, or you are even having not a local disk, you're having a storage area, a SAN, monitor it as well. It's very good that they are up to date, that they are performing, and that you take a good eye on the system. Kafka is living in another ecosystem, so it's good to monitor how the other people is behaving. To monitor this, you can use Control Center, and you can use as well Datadog. That's a great tool for monitoring. Before we are done with this story, I want to raise a couple of things. For monitoring, it's very important, the alerting. I've been operating Kafka for many years right now, and alert fatigue is a thing. So I try to have this rule when I don't have more smart system to handle alerts, 60-80. 60, something I have to do, but it's not in a hurry. 80 is something I have to run out right now. The 60-80 rule is very powerful for handling alerts. And here's like a embrace from the field, always raise meaningful alerts, otherwise your operation team is going to start ignoring them. And in Kafka, some of the times the alerts are a correlation. So are not just one metric, are this metric together with 2 more. And this is what makes nice charts and group charts, and especially things like applying time series analysis, something very powerful for Kafka. And that's all. I hope it was helpful. I'm Pere, I'm a solution architect at Confluent, and yeah, I hope this was very helpful for you. Thank you.